Hi, welcome back. In this lecture, I want to describe the potential performance benefits we can achieve by using in-place operation in Python. I want to describe when it's convenient to use in-place operation and where the performance coming out from the in-place operation. By the end of this lecture, we'll be able to describe the cost of a memory allocation and describe how we can avoid memory allocation by using in-place operation. We'll be able to evaluate the cost of in-place operation for small and large matrices, able to describe the performance advantages and disadvantages for in-place operation. Basically, when it's good to use them or not to use them. Let's talk about a topic that I've been discussing before, that is the cost of allocation and why allocation cost time, cost execution time, and cost performance. We know at this point that allocation impacts the performance. What is the reason for that? Well, the reason is that any memory allocation results in a request to the operating system. Basically, we need some piece of memory available for our array, so we make a request to the OS that is reserving an available chunk of memory for our data. Why this cost time? Well, the request to the OS generates quite a lot of effort. And this, if we think how different is the performance loss, for instance, when we have a cache miss or we need to fill the cache, is quite different. Filling a cache or a cache miss is a hardware routine that is optimized on the motherboard. The allocating memory operation is not handling by hardware. Instead, is handled by software with a requested to operative system. Allocating memory requires talking to another process, in this case the kernel, in order to complete. So memory allocation costs time. One technique that we can do to avoid multiple memory allocation is to do a pre-allocation. So we start our simulation, we start our code with all the variables and arrays that we're going to use. So we allocate at the very beginning, and then we take care of using all those variables and arrays that we pre-allocate at the beginning of our code. So we pre-allocate some scratch space at the beginning of the code, and then we use only in-place operation. What is an in-place operation? An in-place operation is operations such as plus equal, star equal. So are those all operations that use one of their inputs as their output. So we basically add it up or multiply and put in the output directly in the input. In all the in-place operation, we don't need to allocate space to store the results of the calculation, since the output goes directly in the input. So that's why they're called in-place operation. Let's look at an example of in-place operation. So for instance, we can have use a NumPy, and then we create two matrices, array 1 and array 2 of size 10 by 10. To check if a memory allocation occurs or not, we can use the ID function that we have been looking at before. The ID function indicates which section of the memory is being referenced. So it basically returns a reference of the particular object we are looking at. So in this case, we are allocating a 2 array, and we fill it with the random number. Instead of being arrays, is improper. These are matrices of 10 by 10. And then we check what is the reference for array 1, right? And we get this number here. Remember, this is a reference, can be meant as the address where our data is. If we do this in-place operation, we take array 1 and we add up the second array, array 2, that basically added up this value to all this value to this value, and then we take what is the reference of the new array 1, and we note that the reference is the same. It means that we have the same reference. It means also that we didn't allocate any new array to store the results. We just use the initial allocation and then we don't reallocate it. In case we express the very same operation, basically summing up array 2 to array 1 without using the in-place operation, if we do that, we do array 1 equal to array 1 without using the in-place operation here, and we sum it up to array 2. We take the results of array 1 and we take what is the reference in memory. We will note that the reference in this case is different, right? So here we have the end 424 and here we have 792. So these are two different references. This also means that here we create a new reference, so we had a new allocation, right? And this allocation, remember that it takes time. Let's look at more into detail what is the cost and in terms of time of in place operation or non in place operation. In these slides, I have two cases. One so-called large matrices that where I take two matrices of 100 by 100, still rather small. We can also take 1000 by 1000. What large means in this context? Well, large in this context means that it should be larger than the size of our caches. We will talk at the end of this lecture about this. And then we take small matrices. So instead of taking 100 by 100 like we took here, we take 5 by 5. In the first case where we have a large matrices, we have the two arrays that are large, and then we time first the non-in-place operation. So we do array 1 equal to array 1 plus array 2, and we get 6.45 microseconds. I'm using the magic command time it in IPython. If now we time the very same operation but using in place operation plus equal to array, we see that we get 5.06 microsecond. So see you get 10-20% of the improvement by just being more concise and use the in place operation. If you're looking now at the cost for small matrices, for instance 5 by 5, and we do the in place operation, we see here 518 nanoseconds. And if you do the in place operation, we have 1.18 microseconds. That is roughly twice, right? So in this case, in place operation is good, so it's okay. And for a small matrix, it's not okay, so it's KO. So to summarize these slides, we see that using in place operation gives us a 27 speed up for an array of 100 by 100 elements. And we can actually measure and we see that this margin will become larger as the arrays grows. So as the matrices grows up, the advantage of using in-place operation will increase, since the memory allocation will become larger. However, when we use small matrices, we see that this is not working anymore. When the arrays are smaller and the two inputs and the output can all fit into the cache, the auto-place operation are faster because they can benefit from vectorization and caching. We can go back to our usual problem of the diffusion problem code, and in the previous lecture we expressed the Laplacian operator as a vector operation using NumPy. What we can do one extra step and express the Laplacian operation as in-place operation. So you see here we do star equal -4, and that will have the contribution of each grid at the point, and then we added up all the contribution to out from the neighbor points. Let's look at the perf results when we are using the in-place operation in our diffusion code. So comparing the performance metrics, removing all the spurious allocation coming from the fact of using out of place operation allow us to get quite a large performance improvement, right? 30%. So this speed up comes partly from reduction of in the number of cache misses, but mostly from reduction from the binary faults. Remember that the binary faults are really those counters that tell us the cost of the memory allocation, right? Because we need to talk to the memory and reserve some memory the first time we want to use the arrays. So if you're looking at the perf results, there are two main points that I want to emphasize when looking at optimization of using in-place operation. One is the cache, right? You see here we have quite a good cache results. We have 20% only of cache misses. We can do better, but previously we got 25%, so we got certain improvement coming from a reduced number of cache misses, but most importantly are the minor faults. So minor faults are really correlated to the number of allocations. So the number of faults is reduced considerably. To summarize, we should always consider allocation as an expensive operation to complete. In-place operation allow us to avoid the reallocation and decrease the number of minor faults. In-place operations are advantageous when the matrices or vectors are large, so they do not fit into the caches. We should not use in-place operation when the grid size is small. This is not advantageous because the data can stay in the caches, can use vectorization, but with the in-place operation we cannot do. This is the last slides of the lecture, and talk to you soon.